Thank you. Excellent. A little bit of help. So, welcome everybody. I'm Peter Corley. I'm the head of the Mechanical Engineering Department. Very warm welcome to you all, particularly our guests from elsewhere. Daniele's friends and family and collaborators, so it's great to see you all. So, inaugural lectures are great occasions. It's an opportunity to celebrate achievement, which is something paradoxically in universities we often don't do. So, inaugurals are a great occasion to do that. There's also an opportunity, of course, for colleagues who are not in Daniele's field to learn something about what he does, which is great. So Daniele has been with us since 2006, coming by way of a M-Eng in Bari and then a DPhil at Oxford. Then he saw the light and came to London, so which is very good. Daniele's fantastic record of achievement. So he's currently an EPSRC Established Career Fellowship. I need to get that one right. So this is EPSRC's Premier Fellowship, so very, very prestigious to get to Daniele's career stage, which is fantastic. A measure of his breadth is that he's also won an Imperial Award for Research Supervision and also an Imperial Award Medal for Teaching. So he's one of those unusual characters who actually really does excel in all aspects of the academic job. And the other thing to say about Daniele is that he's a head of department's dream, because he's one of the very few people who will say yes. and say yes unequivocally and with a smile on his face, without too much gritting of teeth, or so it appears. Either that or he's a very good actor. So, Daniele, it's a pleasure to have you in the department, and we very much look forward to hearing your lecture. So, over to you.
Thanks, Peter. Right. I have to say, just looking at the crowd and looking at all familiar faces, I really thought the first thing to do is to thank you to be here. I mean, I wouldn't be here without you, and I think that's the first message I want you to get from this lecture. And the second thing I want to start conveying in this lecture is that, given the mixture of the audience in terms of background, I'm going to try to cover not only some of the technical advances made in the field, but also some of the personal aspects of my career, including, for example, why I dressed up as Mario and gave a lecture at some point. But the idea is that, if anything, if I manage to do something, I'll take probably my last opportunity to get someone like my wife to understand what I do at the end of this talk. So to start, obviously, some of this might be a bit low-key for tribologists, but certainly taking a broad view to the field. So I'm going to start by telling you what tribology is, simply because some of you still don't know what it might be. And I'm going to go down to how I've actually, through my career, explored various aspects of tribology, including friction, obviously. So, obviously, the first thing to talk about in tribology is how beautiful a science it is. Tribology is a science that studies interfaces. And so anything that moves and has got two things in contact is covered by tribology. Now, obviously, that makes life fairly easy for someone who's looking for something to do, but obviously very complicated because there's loads of things coming your way. And obviously the various aspects, obviously if you look at transport, is a classical application in tribology. There are plenty of components in any things that moves that require understanding of friction, lubrication, the way components get damaged. If you look at the need for new energy sources, even things which are renewable energy, such as wind turbines, require quite a lot of understanding of the components that make them run. Anything that is in the energy field deals with components that require knowledge of tribology. Not to mention, obviously, the fact that as I'm moving, I'm stretching my cartilage and moving a lot of joints in my body. And there is a lot of understanding in looking at the friction between joints that goes in healthcare, but also some more exotic application I'll speak about. And obviously there is quite a lot of work, especially in the recent years, focusing on the importance of looking at machines getting smaller and smaller and understanding how they work. And there is where friction plays a key role. Now, obviously, in this panorama, there is lots of challenges, and tribology is in all of these. And you can almost try to look at the field of tribology in the broadest sense again, but this time looking at things that are more classical applications in tribology. And this is the application I started with my PhD when in Oxford, in collaboration with Rolls, we were trying to understand how the detachment of these blades come in these engines and trying to avoid it. And this is a typical phenomenon where you got blades that potentially run against the disk, and if you're not careful, boom. The idea is, obviously, that's a question of reliability. You want to make sure these things are safe, and there are lots of components. There are billions of these components in everything that moves around that you want to make sure it's safe and lasts very long. Now, the other classical field of tribology is the one in which lots of people have been trying to understand how surfaces interact to lower friction. So lots of people want to save energy, we want to reduce friction, and you can do that through different things. You can actually use lubricants and improve the lubrication between surfaces, or you can change your surface itself by using coatings or texturing to modify its performances. But obviously today, and especially looking at healthcare issues, there is many other areas in which tribology is important. So we've been looking at the way joints work, both artificial and real joints, but also you'll be surprised how important tribology is when you do neurosurgery, because you need to understand how tools, for example, interact with very soft matter. And finally, obviously, there is, as I said, again, you go back into the fact that there's more and more applications coming from the smaller scales, and understanding how friction, the nature of friction and how it comes about with different manifestation at those scales is very, very important. And in fact, I'll start my cruise here through the technical part of the talk, looking at various aspects of contact mechanics, but also tribology in the sense that taking any element that has got parts in motion, in this case I'm taking a bearing because there are billions of them running in any of the things that you move. If you zoom into the contact, if you zoom into the parts that actually rub between each other, you soon realize that these components, A, have got rough surfaces, B, they usually have a lubricant between them, could be obviously different type of lubricants. But actually, what happens at the interface here is dominated by things that happen at very small scales. Depends on how your roughness interacts, depends on how your solid deforms, depends on how the fluid moves between the surfaces. And again, you can almost go down and down in scales to think about how atoms interact at those interfaces. And one of the beauty of tribology, which is also actually the reason why it's an exciting subject, is that you need to obviously, if you deal with something like this, you need to be able to understand about fluids, various aspects of fluids. How does the fluid behave under the contact? Is the chemical reaction happening in the fluid? Can you have a certain surface chemistry, and how is that important in your field? But also you need to understand how the solid part of this, so the two surfaces themselves, how do they deform? Do you get damage? Do you get wear? Why do you get wear? And can you explain how the surface evolves? And the beauty of this is that obviously to be a good tribologist, you need to start thinking about how to model or how to understand better how fluid and solid interacts. And to do this, you need to have the broadest possible background, scientific background. You need to combine physics, chemistry, engineering, and biology if you want. And if this is the scenario, I joined the group in 2006, and I joined a group where the majority of the people in the group were experimentalists. And if you just looked around the lab, you will soon realize that people were doing experiments at all sorts of scales. So here is a map of time and length scales. And you will get people who were doing experiments on entire components. You will get people who will do experiments, laboratory experiments, looking at smaller components. And then you were getting loads and loads of experiments trying to characterize what happens at the interface in different parts. And in fact, one of the things you realize straight away is that lots of people tend to interact more when you go down in scale. In fact, you get a lot of material scientists interested in tribology when you start trying to understand how the material evolves or what happens to the fluid in contact. But also, biomaterials and biology actually has become more and more prominent in this area. So you get a lot of people with a biology background joining this. But finally, you also realize that the physics and the chemistry that underpins the mechanism in tribology, it's all happening at the smaller scales. And that's where most of the contributions from this area come. Now, the idea is that I joined this group, and all I've set up to do in my time here is to build the equivalent with models. So throughout my career, I started looking at models at different scales, and more recently at connecting models from the smaller scales to the larger scales. And here we're talking about something that it's what I'm currently doing, which is trying to bridge all these skills and combine these techniques into a unique tool that probably people can use in different areas. And it's been a bit boring so far, so I'm going to give you a bit of a personal trajectory in this. So my personal trajectory went up to down. So according to my mom, I started getting an interest in cars and airplanes about that age. I thought I wanted to be a basketballer, but that's a different matter. That's what she said. She's not here, so she can't testify, but I'm sure she will be hearing this soon. And then actually, yes, later on I did get my interest in the larger type scales. And those of you who have never seen me around an equipment or lab, they will be surprised to see me doing experiments in Oxford there in my days of PhD. David and John definitely know I've been there. Now, later on, I decided that, in fact, in order to go down in scales, I needed computers, big computers, and students, clever students. And both of them came very handy. And I think with maturity came the realization that models on their own are not really needed, so I fakely put back my gown and showed that experiments are also important. One of the messages I'm going to try to convey today is that there's no good model without good experiments, and I'm very, very lucky to be here with lots of colleagues who can support everything we do with experiments. Now, on an even more personal note, one of the things I don't really like is to take myself too seriously, as many of you will know. And in fact, throughout the same trajectory, I have tried not to do that. So here is some of my appearances in Oxford as a PhD. And depending on the settings, I was changing the tone of things, obviously. And then actually later came the realization that this job obviously comes with being able to multitask. So this is an example when I realized actually multitask is needed. And finally, I even tried more recently to push the boundaries. And here it's here is the evidence that actually there's nothing that should be left untried when it comes to education and inspiration of the youngsters. Now, so that's about my personal trajectory. So let's go back to the serious stuff. One of the things I'm going to do now, and I have to apologize for those of you I'm not going to be able to show the work of, but I'm going to try to give pills of the research we do with different scales and how we've managed to actually make some breakthroughs in this area. So I'm going to start from the bottom of the scales, going all the way up. And so some of the examples of the work we've done start with first example is looking at some work we did on marine diesel engines and try to understand the effect that changes in the regulation have had on these systems, and try to really look at the system, which is very big. Look at this is the size of a person, and we're trying to understand how lubrication of these systems works. And one of the things that happened as a consequence of the regulation changes is that actually people started looking at changing their lubricants to avoid corrosion, because the changes in pressure and temperature in your engine has actually caused changes in the way the system behaves. And in fact, one of the things that people realize is that if you don't change your chemistry accordingly to your operating conditions, you can get corrosion in this system. And one of the things we explored, therefore, at the molecular level is the effect the change in the molecules you got in your lubricant have in terms of affecting inhibition of corrosion. And here is, for example, looking at some detergent molecules and the way they develop themselves in fluids. And actually, once they've formed what we call a micelle or something like this, how they interact in a bath of oil, let's say, with a molecule of water to try to stop acid reactions in your system. And here you can see that with some very clever and long simulation on a computer, you can try to explain the mechanism by which these things behave. And you can start actually trying to understand how to design these molecules and how these molecules interact with different pressure and temperatures in order to improve the performances of this system. And obviously, we're very pleased because we managed to explain for the first time how the mechanism of penetration of these molecules happens, for example, in interacting with water in solutions. And that led to my first cover. Now, it's beautiful, but an email of one of my third-year students made me realize that there is some room for improvement on the covers. So hopefully the next one will look a bit more like this. So I think there is room for improvement. We'll see. Now, that's the first example. And again, I'm not going to go into the details of the science because it will take half an hour for each of the topics, and I've got way too many I want to cover. The second bit I want to speak about, again, goes on to the realm of understanding lubrication from the fundamentals. And one of the things we set up to do with James, who's sitting over there, and other people in the group, is to understand how, for example, using some specific additive molecules and linking them to your lubricants, you can affect the frictional behavior of surfaces. And here we've explored the effect of specific additives again, organic friction modifiers, when they are absorbed on the surface. Here you're looking at very nice iron oxide surfaces. They don't really look like that, but in a computer model they do. And here you've got absorbed some fancy molecules that are put there to reduce friction. And the idea of this study was to try and understand what's the mechanism by which you end up reducing this friction. And to do that, we did a lot of different simulations, starting from looking at how, if you take two surfaces and you squash them together, whether or not they've got some roughness on it, and you try to shear them, once you apply very large pressure, you get a certain frictional response. Now, what we did, we studied conventional molecules. We started doing a lot of simulations. We did the best we could do with state-of-the-art molecular dynamics simulation. And literally what we wanted to understand is, for example, the effect that how many of these molecules you get on the surface affect the friction. So if I try to put as many as I can squashed on the surface of this molecule, does that help? And the answer comes from the simulation. If you look at this simulation moving, you're applying a load over the surface, you're shearing it, and you're looking at the friction that comes out of these systems. And it's a bit like looking at nice al dente spaghetti here and badly cooked spaghetti over there. You expect the badly cooked spaghetti to be much gluier and giving higher friction. And it's actually exactly what happens. You look at this system and you see that if you look at the maximum absorption, so if you put a lot of these polymers on the surface, or if you decrease the quantity, you have different kind of effects in terms of shearing of this lubricant. And in fact, what happens is that the lowest friction happens when you have a lot of those. So you create a very structured systems, and the slip is confined between the layers of these two layers of brushes. Whilst if you go down in terms of coverage of the surface, you start getting that there is this intermingling between the molecules that stops you from doing easy movement between the surfaces. And in fact, that is what was also found with the experiments. And at an intermediate level of interdigitation, where you got the lowest coverage, where you start getting back the friction you will get if these molecules were not present. And in fact, these seems to agree not only in terms of values, but also in terms of ordering of different molecules with the experimental results that in the group were obtained by other people. And that's again sending the message that we tend to do models that try to explain what we see experimentally, which is actually one of the key themes of this. The other thing we're doing more recently, and I think that's very difficult to see, but basically we're looking at covering different structures, different molecules, and see how these different molecules work. And again, the idea here is to try to do some simulation that show that different type of molecules in your system have got different effect on your friction. And very recently, we looked at modeling real molecules between surfaces. This time, we're not looking at very tiny gaps like we were doing before. This time, we're looking at much larger gaps. We're looking at the response of large quantities of fluid between the surfaces. And we're trying to compare our experiments, our results with the experiments done in the lab again. And one of the things that we are interested in is to try and understand what is the effect of pressure and how fast you slide the surfaces together. And one of the things we managed to do, which is fairly impressive in some respect, is that we managed to model these things with atoms and molecules explicitly. And we managed to, in a way, push the models to the scales that never had pushed these models to before, and see that actually what we see in the experiments, which for very long chain molecules is that you get a low friction that rises up with the increased shear rate, can be actually mimicked by the models that we developed. And this can be done for all molecules, but also you can capture the subtle differences between the different kind of molecules you have, because if you don't have a long chain molecules, we got something more bulky, you can see that there is again a match between, at least in trends, between the experiments and the models. And this is shown to be a function of what happens to these molecules when they are sheared. And in fact, as I said, the simulations are the key. If you look at this simulation, you'll find that the structure of this fluid, when it's confined between these two walls, is responsible for the different behavior. And in fact, for things that are much bulkier, you get that this is all due to the shear localization. And this shear localization happens much earlier for this type of molecules, which are bulkier, than this type of molecules that tend to shear more easily. And again, this is the kind of thing that we would like to verify experimentally, and that's why, in fact, we've done some experiments through Janet's group that actually have shown similar things on different molecules, and we're going to try to match explicitly with our models. Now, that takes me to the end of that scale. And again, it shows how important looking at what happens at the atomistic level is. And it broadens the spectrum of problem because we're going to go one scale up. And again, I'm going to pick 3 simple examples to go through. The first one is looking at a particularly relevant problem for automotive, which goes into trying to understand why if you texture a surface, for example, in a cylinder liner, if you got a car, you got your engine, you're trying to reduce the friction in your cylinder, one of the most important things to look at is to change the surface so that you reduce friction. And this was also prompted by the fact that we have a collaboration with people who could machine and different type of surfaces. And again, the inspiration from this came from experiments. Here is a rig that Tom Bradioff has developed in the lab. And this rig is really trying to probe what happens at the interface between a piston and a cylinder liner. And here you've got basically the cylinder liner replicated with a transparent surface, and there is a piston ring running against it. And the beauty of it is that those surfaces, which are made of sapphire, are transparent. So you can look through, and you can texture them. So the idea is that with this system, you can try to model what happens when you slide one surface with respect to the other. And the response of what happens is very much depending on what you do to these surfaces. And here we're talking about looking at the microstructure of these systems where we're talking about pockets in the order of micrometers in size. So we're talking really about how can a micrometer-sized pocket change the behavior of this system. And I set up to explain this by, first of all, looking experimentally at what you see. And if you can look through these surfaces, so let's say your sapphire window is here, you look through the surface, these surfaces are moving with respect to each other. You see that if you monitor this, you see that there is interaction between the pockets and the fluid. And in fact, you can see pockets of bubbles forming the inlet and the outlet of this system. And these obviously change as the velocity changes. And we have then since managed to explain this by looking at models that explain exactly what happens when a pocket traverses a contact, where you see that there is change in the fluid, there's cavitation happening in the fluid. The fluid is changing phase. And as a result of changing phase, there is a change in the way the system takes on pressure from the lubricant. And this obviously it's very important because it explains what happens through these pockets can be explained with models. And again, I'm not going to go into the details of this, but it's the interaction between this pocket and the fluid that is responsible for the reduction of friction. And it's been demonstrated in different kind of problems, but also there are different effects happening at different speeds. So imagine you're going with your piston at different speeds. At different speed, you've got different buildup of fluids between your surfaces. And our model also allowed to explain why at different speed you've got different effects. And in fact, the presence of this texture can reduce friction quite dramatically. These are the experimental value from Tom, and we get models that explain exactly the same trend. So that's, again, a bit more classical. Let's look at something more funky. Now, the funkier application comes from my colleagues in China who decided that wanted to do something biomimetic and decided that they wanted to look at eels. And from experimental evidence, squashing the heel and doing something to it, they worked out that the very slippery surface on the heels is due to the presence of mucus, which is coming out by osmosis from pores. And inspired by that, they developed something similar. So they took a system which has got pores, and they infiltrated this with polymers, and then they cross-linked these polymers to form an hydrogel. Now, when they cross-link this polymer to form an hydrogel and they're peeling off the excess hydrogel, they ended up with a series of polymer heads, hydrogel heads, sticking out to the surface. Now, it turns out that then if you put this material in contact and you try to slide something over it, if this liquid between these two surfaces has got a certain pH, you can get very low friction. You basically, you don't need any force to make this thing slide. Now, not only that, it looks like if you change the pH of the solution from very acid, very low values, to very basic, high values, because of these hydrogel swell and diswell, there's a chemomechanical action into these hydrogels, you can change your friction coefficient instantaneously almost to go from very low to very high. So you've got a way to switch friction in the contact between these systems. And then our theory showed that this is due to the fact that for different pH, and I'm not going to say what this hydration is. Basically, the principle is very simple. If you go very high in pH, you start swelling your hydrogel. Swelling hydrogel means you've got more lubricants available for you to replenish the surfaces. Friction goes down. And in fact, can go down dramatically. You can talk about friction changes of 2 orders of magnitudes just by changing the pH of your solution for these systems. But the good development of this comes from the fact that once you know that you can tune and switch your friction between surfaces, you can think of tons of things you're going to do with this. So one of the things they did, and we did the theoretical explanation for this, was to create this time a system with 2 of these surfaces on each side. And the idea was that thanks to these hydrogel, which are actually very fibrous, and having them on both sides, you can generate a structure like this, and you can think of putting it between 2 surfaces. So imagine you're now placing this system between 2 surfaces, and you're squashing the 2 surfaces with a certain load. Now, simply by changing the pH on one side of the membrane or the other, you can lower the friction. So therefore, if you are in a situation where you've got low pH on both sides, you can hang any weight you want to this system when it's squashed between and hold quite a lot of load. But then if you actually go and increase the pH dramatically, you get a very slippery system. So your adhesion forces, your weight carrying capacity goes down drastically. And in fact, there's an experiment showing here that with the same kind of tweezers, if you put the same type of apparatus, you change the pH of the solution with which you wet the system, you get completely different holding capacity in the system. And that, I think, is a nice way to show nice engineering through friction. Now, the other things we do, and again, it gets a bit fancier in terms of videos and things, is another example. This is Lee's work in collaboration with Berend and Fabian, looking at bubbles. Now, someone might say, what the hell is bubbles doing with tribology? There is plenty to do. Lubricants, foam. And one of the things that we set up doing here is why do you get foams, and how can we prevent foams if we have them in lubricants, for example. And in order to solve that problem, the first thing we need to understand is how foams behave. So that's a video that won Lee a prize, showing the mechanism by which foams evolve. Here is looking at a bubble of this side, from the side, and you start looking at patterning and the patterning evolution of these bubbles, and you try to explain the coarsening behavior due to the chemicals of the surfactants that you have in these fluids. This is just a soap bubble that you can get in your system. And in reality, some of these coarsening effects can be explained through models. And if you look at another bubble here, if you now this time you've got a bubble in front of you, and it's very large, and you look at the way it evolves, some of these patterns, again, can be explained mathematically, and that's where the theory comes in, because they depend very much on how much of these surfactants, how much of these molecules you have while you form your thin layer for the bubble. And the mathematical theory that we've developed tries to explain why you start seeing these patterns forming in the area where the bubble is going to break. And this is one of the achievements that actually explains why in different regions, when you have a bubble, you have different patterns that evolve in time. And again, this is very interesting because it tells you the dynamics of the flow and how important it is in understanding the breaking. Now, finally, if I move on to larger scales, there is a couple of things I wanted to take you through. One of them is, again, going into classical application of tribology, and specifically is looking at high-performing engines. So the first thing that I've showed you so far is we've taken you from the smallest of the scales all the way up to larger scales. So obviously, as an engineer, you're interested in understanding how components work. So one of the things we do is trying to predict the behavior of full component systems. And again, I'm taking an high-performing engineer from Ducati and trying to understand what happens in the bearings of these systems. And you need to understand that when this motorbike cycle, if you've ever been on a motorbike and you listen to the engine, there's a lot of dynamics going on here, and the load transmitted through this component is very high. So the secret to go and understand what happens in this bearing, so I'm only interested in part of this engine. I'm interested in what happens at the interface between different components. The way to do this is to understand what happens at each individual component by looking at the tribology of it. And in order to do this, you cannot just study the entire system. It's too difficult. You need to find a system to take, say, a full component and look at the regions of interest. And here, the region of interest are the contact between these element and the pin that goes through it, because that's where the rotation happens. And obviously, this is affected by very large loads, and these loads are varying in time because your engine has got quite a lot of varying loading scenarios. So the model that we use takes information from the full-scale system, the loading for the full-scale system, and then looks at the details of what happens in this bearing. So this bearing is deforming in time. This bearing has got some pressure building up as you load it with the lubricant between them, and also has some cavitation forming. So there is some bubbles forming as you go around the system. Now, the combination of all these things, it's what governs the performances of the system in terms of friction, but also in terms of the way this system fails. And in fact, if you look at this component a bit more in details, and especially if you look, for example, at a cut through this system, I'm only looking for, if this is the bearing, I'm now slicing it through and putting it on a plane. If I slice it through and I look at what happens in this plane, I can look at the time average information of these systems and start, for example, plotting areas in which the pressure is the largest. So that's where you expect the larger loads and stresses to be. Then I can look at places where I might get direct contact between the components, which are also of interest. But most of the time, the thing which is most important to understand damage induced by cavitation, which is bubbles forming in the fluids and then imploding back onto the surface and therefore causing damage, it's trying to understand in time what are the regions of your bearing where this formation of bubbles and collapse of bubbles happens most often. And through a lot of this simulation, one of the things we came up with is what we call the cavitation damage index, which tells you exactly that. It tells you how quickly and how fast these bubbles form on the surface. And these seem to correlate very well with the regions where these bearings add damage, and therefore enabled us to solve a very important technical problem on a full component scale for these systems. And again, this is on a very traditional type of application. So let's look at something a bit different. Lots of the things that we've done in different applications touch on to different fields. And one of the things that I've been getting more and more passionate about is looking at biological application. So one of the things that are of interest and very much important in the last years, in the past decade, has been to try and understand how friction develops between joints, and it's cartilage and cartilaginous tissue between joints. And this can only be understood if you understand what happens to the cartilage while you're rubbing it. And so one of the things we've set up to do a few years back is to try and get a better understanding of the working of cartilaginous tissue. And this has been done through models, trying to understand the fact that this tissue are composed mainly of water, and this tissue cannot operate if you assume that they are actually solid. So the way that this tissue operates in is coming from the fact that when you imagine you have a cartilage tissue here, you've got a bone here, and you're trying to slide something over them. Now, if you slide something over a material which is porous, has got fluid in it, and you're trying to actually squeeze this fluid out, the dynamic of the fluid going in and out of this tissue is what governs the way the tissue deforms. And that can be explained why you can get very, very low friction in cartilage. We're talking about almost zero friction in cartilage when you walk, and that's the reason why all of us, most of us, don't develop osteoarthritis in the early stages. It's because of the fluid flowing through this porous structure that maintains the load. And what that led to is the development, or helping the development, of synthetic tissue that could potentially replace our cartilage when it gets damaged due to a sport injury or other different potential issues. And the other things we did, once we understood the concept and the working of these systems at the smaller scale, we ended up doing full joints models, where these full joints model account for the real working of the cartilage and look at the dynamics of the joint. And one of the things we managed to work out the first time we worked on this was that if you subject this joint to a loading cycle, this is a typical loading cycle. This is one cycle. As I'm walking, I've done probably hundreds of them by now. You see that there is a change in the way the pressure in your system develops. And this pressure tends to diminish because the system tends to relax as you walk. And in fact, sometimes walking is one of the best cures to avoid arthritis in some respects. The last example I'm going to show you at this scale, again, goes back to biology, and it goes back to trying to solve an even harder problem. And this time, inspiration came from Ferdi and his group. Here, Ferdi has set up to try and contribute to solve a problem in neurosurgery, which is trying to operate on glioblastomas, which are actually tumors in the brain. And the key innovation of the ideas is that in order for you to be able to access areas in the brain and being able to operate or reduce the tumor, you need to be able to access areas that you can't really access in a straight trajectory, but you would ideally like to go around to avoid critical areas of the brain while you do that. And to do so, Ferdi's group have developed some very clever techniques looking at wasp and the way wasps inject their eggs into wood. They have developed something very interesting that allows you to navigate one of these catheters into materials and avoid obstacles into it. And that's where our collaboration started, is where Ferdi realized that some of the modeling, the understanding of how this goes through the material, and some improvements to the understanding of the materials itself, being brain tissue, a very difficult material, could have helped. And that's where I come in. We try to do quite a lot of work to characterize brain tissue, understand if once we know brain, special phantoms can be made so that we can mimic the real behavior of brain, and also understand with models how you can predict the behavior of this system, which are phenomenally complicated. And we started by doing some very nice work on real brain. This is a human brain. And the only way to characterize a human brain is to be lucky enough to have samples to analyze. And from there, you come up with a description of the way they behave mechanically. So if you squash them, if you shear them, what is the behavior of this material? And that actually led to discoveries, thanks to the work of Francesco, Antonio, and other people in this room, of a material that potentially could mimic the mechanics of brain. And that came from the same route almost as the material I've shown you before for the heels. It's an hydrogel. So you get polymers. You get polymers in certain quantities, and you combine them to create a material which has got a certain microstructure, porous microstructure. Now, brain is composed mainly of water, and the way it deforms depends very much on the way water is dispersed into this material. So the material we developed creates this network through which water can pass through, or spinal fluid can pass through linking different molecules. But the idea is that once you've made this material, the real breakthrough was, can we make this material available to people so that you can create phantoms from real patients' MRI? So you can imagine you take an MRI of your patient, you do a specific procedure with the 3D printing to create a negative of your brain, then you actually cast your brain or print your brain actually to create a real structure that resembles that. So you can think of this as being a potential application not only in understanding how the brain works mechanically, but also in training people. So if you get someone who can train on a material which looks and feels very much more like brain, you avoid quite a lot of issues, ethical and non-ethical issues in the training aspects. But the ultimate aim here is that we wanted to see if this material actually behaves like brain. So what we did, we took that into an MRI scan, and we scanned it. And one of the things we were interested in is if you see, as you see in patients, that when you turn the patient, you do a craniotomy, and you wait for the tissue to move and relax, we have the exact same deformation as we see in patients. So do we see our material deflating, shifting, as real brain does? And the answer is yes. We could track through some probes the deformation of this material. And one of the most intriguing things we could do, we could reproduce through models the shift of our materials in the skull. And that gives a sort of two-way comparisons with our model, showing that our representation of brain, or at least of the material that we think reproduces brain best, is actually an accurate reproduction of reality. And obviously, the other step that I've not shown you is that we've done quite a lot of work also to try and understand how things go through this material, which is far more complex. Certainly, one of the accolades I got from this is that I managed to get one of the best prizes for an academic is to give a talk in a pub. And there's been times when I was giving a talk where I wasn't very sure what was the beer, what was the brain, so I got very confused at some point. But certainly, I guess, I've shown the relevance of the work to different people. And to go back to this brain issue, what I've shown you is not the end of it. In fact, as I said, it's much more complex than I made it. So at the moment, we know that taking a brain, we can look at the deformation of it. But as I said at the beginning, our idea is to move this catheter through the brain and deliver maybe some drug at some point to this brain in a way to maximize its effect on the tumor. And to do that, it's not just enough to know how the brain deforms macroscopically, but what we're now set to do with Andrea Zench and other people in this room again is to have an understanding of how the microstructure of the brain affects the fluid flow if you have something injecting into it. And this takes us into the realm of actually, again, looking at the microstructure of these systems and how the microstructure affects the performances. And this is actually the idea. If you get a scanning of the microstructure, you can actually understand better how this drug gets delivered to different parts of the brain. Now, having taken you through this whole journey, one of the things I want to mention, and is the end of the technical part, is very simple, and it's saying, okay, we've done all of this. We know things at small scales. We know things at intermediate scales, large scales. Now, one of the key things to do in our area is to try and link up these things at different scales, and there are different ways of doing it. But one of the things I'm going to show you that we have recently developed, and it's a very interesting way to do things, is the following. I've shown you that I can model with atoms and molecules what happens near the walls. And I've also shown you that we can model fluid flow in a continuum way. And why can we not then try to link these two types of modeling into one model combined? So one of the things we've been working on, again with Dave, Ed, and Edu around here, is to try and develop a technique that allows us to model atoms and molecules where we need them, if we need them, together with continuum description, which are much less expensive computationally, and therefore can be used to explain what happens between surfaces when you slide them. And that has led to the development of techniques that now can be used to study very large systems with a very small computational resources, because the computational resources just used to explain what happens here. Now, one of the movies I'm showing you here is the movie giving you two surfaces. So there are two surfaces with the top wall moving. Now, if you know fundamental of fluid mechanics, you know that if this is a Newtonian fluid or a very simple fluid, you would expect that as you move one wall, in a steady state, this is a profile of velocity. You will get a straight line. Now, that is if you have a fluid which doesn't have any structure or doesn't have any particular properties. But here, for example, what we did, we put some polymer brushes on the surface. And here you can see that the effect of the polymer brushes here is to change the fluid dynamics of the system by switching the point where the velocity profile goes to 0. And this has a profound effect on the flow above. And obviously, we're trying to understand how this can be used for much larger systems than just a simple system with molecules. Now, I hope I conveyed my my pleasure in working in this area. One of the things I hope you've gathered is that to study this phenomena, you need to know quite a lot about different areas. So you need to know how fluids move and be able to explain their interactions. You need to know how things behave near the walls. And there is a plethora of things that are still to be explored. And this makes really this area a fantastic area to work in. And the final development that we're trying to do is to combine all of this into something which is a software tool that people can use. So we have tons of these models developed in different areas, different scales. And one of the targets I have for the next 5 years to come, at least, if not 10 or 20, is to try and combine them in a unique tool that people can take and use, being them academics or people in industry. And this will actually try to combine all these things into something that you can use as a package and something that you can operate without actually knowing all the machine that is behind. And with this, before acknowledging everybody, I would like to, first of all, do an acknowledgement to my wife. Who has certainly aired a lot of my excitation about tribology in the years, especially where there were lots of deadlines and things to finish and less time to spend with her. But I have to say I wouldn't be where I am without their support through the last 15 years. And with this, also, I have a list of everybody. If you can find yourself there, I've done a good job last night in trying to put this together. There's a lot of people involved with this. Everybody sitting here, the majority of you, has had something to do with what I've developed. And that's what makes me very proud to be here and very proud to see this room full of people. That's the current group, or part of the current group behind me. Obviously, this wouldn't have happened without people sponsoring them or me. So there is quite a lot of research funding coming through grants or through partners from industry, different sponsors. And at this stage, I guess I'm really done. Thanks a lot.
So, Daniele, thank you very much. I fear you've lost some people a lot of money there, because there were those of us who were rather betting on you overrunning rather. So
Yes.
and you failed to do that.
I failed to overrun, yes, I know.
So it's my pleasure now to call on David Hills from Oxford to give a vote of thanks. David.
Thank you very much, Peter. Thank you. So it's my duty, but really my honour and my pleasure to propose this vote of thanks to Daniele. It really is very kind of him. Of all the people he could have asked, he's chosen me, and I'm very touched. Thank you. The trite thing to say would be that it's gratifying to see somebody who did a DPhil with one make such fantastic progress and get a proper chair in a proper university. But that would be inaccurate, not because this isn't a proper university and a proper chair, but because it would be too condescending. From the moment we met in the lab, we worked as equals. And it's also inaccurate because although he tells me otherwise, I don't think I was ever his actual DPhil supervisor. Daniele came to Oxford in 2001, and really he didn't do one DPhil, he did 3. He was working primarily for David Knoll at the time, who will also be doing an inaugural lecture here in due course. And that work, as you've heard, was on dovetail routes and gas turbines and fretting. And we met, I think, in the tea room one day, and we hit it off straight away, and we started working on 2 other things. I think the first thing we started working on was cracks and notches and so on. And that would have made another completely competent DPhil anywhere else. And then we also started doing some more basic work on contact mechanics. At the time, Isabel, he used to smoke a lot, so we used to refer to a 2-cigarette problem or a 5-cigarette problem when he would have to go outside and smoke for a while. So that was in 2001 when he came, and of course the DPhil took about 3 or 4 years. So it came to 2006, and he was still with us doing postdoc work, and it was an incredibly fecund time for me because his brain just, as you see, it goes at the rate of 80 slides an hour. So initially, at least, I was reluctant to recommend him to this job. But the right thing to do was to shove him out and get him here on his own. And of course, he's never looked back, and it was completely the right thing to do at the right time. And the progress he's made in the past 11 years is really quite extraordinary. He's gone from strength to strength. It's not true to say that he's ploughing his own furrow. He's ploughing about 15 furrows. in plenty of fields where I know absolutely nothing, the fluids, the bio, the molecular dynamics, and so on. It's all very wide-ranging. And in each of this, he's doing very seminal, enduring work. Not for Daniele, the shortcut or the botched-up reasoning. For him, it's the real McCoy. And, of course, this is being reflected, this achievement, in the award of the chair that we're celebrating this evening. But he's remained modest. All of the work is strictly his. He's not borrowed from anybody else. It's all the fruit of his own brain. And at the same time, as Peter Corley's just reminded us, he's not shirked in his undergraduate teaching, and he's continued undergraduate education to the very fullest of his ability, and with great finesse. And it's on the future of, our futures depend on having good undergraduates. When he came here, we were just resurrecting the International Journal of Solids and Structures, and I was very grateful when he agreed to come and join me on that journal, and I thank you publicly for that now, for the work over the past 10 years or so on that. In recent years, Daniele has shown a great deal of courage. Life's not always been very easy for him. But now I think we want to look to the future. So as I wind up these remarks, I begin by saying that I'm sure I speak for us all when I wish the very, very best to Daniele and Isabel and Angelo and his family, and we hope that things go really well for them in the future. On the professional front, of course, Daniele has just moved to the next phase in his career with the authority that the chair will take. And we look forward very much to significant progress in a number of things in the physical sciences. I don't think he'll let us down. Thank you.
Thank you, David. So that concludes the formal proceedings. There should be refreshments out there for us all to enjoy. So thank you very much for coming, and hope you enjoyed it.